telescope. So it's planned to, it's an international collaboration between NASA, ESA, and the Canadian, ESA is the European, and the Canadian Space Agency. And it's planned to be launched on an Ariane 5 out of Kourou in French Guinea. And the telescope is too big to fit in the shroud of the Ariane, so it needs to be deployed in order to be launched. And it will operate at the L2 Lagrangian point of the Earth-Sun system, which is about 1.5 million kilometers away from the Earth. And the advantage of that point is essentially the extra distance. The Earth's gravity, extra gravity balances the extra distance. So the period at 1.5 billion kilometers away from the Earth is exactly 1 Earth year. So it remains aligned with on the Earth-Sun line. And this allows the sun shield to keep constantly the Earth and the sun, and most of the time the moon, on one side, shielding the telescope from their thermal contribution. These are the instruments. It can take images and spectra in a number of ways, going from 0.6 microns to 28 microns. I will go very quickly. So the telescope, saturation is an astronomy unit that nobody cares about here probably, but the sensitivity I'm giving it in nanojansky that probably nobody cares about either, but nanojansky is a flux unit. A Jansky is 10 minus 26 watts per square meter per hertz. So nanojansky is kind of faint. And 10 nanojansky is what it can get signal to noise of 10 in 10,000 seconds, so 3 hours. So it's a very sensitive telescope in the infrared. And its peak sensitivity is around, this is a typo too, but anyway, this R notation is essentially, this is 2.77 microns. The peak sensitivity is around 3 microns, because the background where the telescope lives is the zodiacal background, which is produced by dust on the plane of the solar system. So it decreases as you go to longer wavelengths, but then beyond 3 micron, the telescope own background, due to the telescope own temperature, starts raising. So 3 microns is the most sensitive wavelength. The near infrared spectrograph is interesting because we want to do multi-object spectroscopy in space on the ground. If any of you are familiar with multi-object spectroscopy, there are 2 methods that people use. One is that you have a multi-fiber instrument where you, with arms, mechanical arms, then move the fibers to the objects, and then the fiber brings the signal to a slit and the light is dispersed. The other one is to use a multi-object spectrograph based on apertures, and you have, for instance, a laser milling machine that cuts little...
It's conceivable the audience would help if you explain that the objects are the distant galaxies.
Yeah, distant galaxies. So you cut these little slits in the metal plate using a laser, say, in correspondence of the object, and again the light is dispersed and you get spectra. Neither of these would work well here. So what we develop is a MEMS, is a microelectronic mechanical system, a micro shutter array that allows you to open the slits where you want them in a way that is commanded from the ground. And this is what it looks like. It's micro shutter compared to human hair there. And this is machined, and it's a very complicated device, in fact, and it's magnetically actuated and electrostatically captured. So when you want to open a slit-let, you move a magnet, all these things flip by 90 degrees, because at the size of these things, a 90 degrees deflection is in the elastic regime. So elastically moved by 90 degrees, The ones that you want to keep open are sent an electrostatic signal, so it's electrostatically captured. And then when you move away the magnet, the others relax to the other position, and the ones that you capture remain open, and you can take the spectra. And this allows you to take of the order of 100 spectra in the places you want. Mid-infrared instrument does both imaging and spectroscopy. These are just pictures of how they look like. And by the way, the reason of 28 microns is that there is a line for molecular hydrogen that is a line that people were interested in detecting, and that's why we push to get to that. And then there is an additional instrument that can take spectra the same wavelength range, and this has also the spectra for studying galaxies and for studying exoplanets, and also has this funny thing which is an aperture masking interferometry that is a trick that essentially allows the telescope to get a factor 2 extra angular resolution that a factor 2 over what a 6.5 meter would normally have. As I mentioned earlier, the telescope is pretty sensitive, so I won't say any more about that unless people ask at the end. So the telescope was designed to do a bunch of things: study first galaxies, study star formation in the Milky Way galaxy, study solar system chemical evolution and the chemical evolution in our own galaxy, and study how galaxies evolve. After we designed it, a lot of exoplanets were discovered from the ground or using the Kepler mission. And so we discovered that James Webb actually has significant capabilities in characterizing exoplanets, so that became a component of what the telescope can do. We only did one little design change to improve its capabilities in that area, but it was already pretty capable. So this is a simulation. This is the Hubble ultra deep field. The thing on the right is a zoom in into that little square. And what I did here is to take the ultra deep field taken with Hubble. I deconvolved the image to remove the point spread function of the Hubble Space Telescope, essentially remove the finite angular resolution imposed by Hubble and convolve it with the point spread function of the James Webb. Of course, the James Webb image may not look exactly like this, because when you do the convolutions, you get, you tend to amplify noise peaks. If you could see at higher resolution by deconvolving, you would save a lot of money by using small. So this is not exactly how it's going to look at. And then I added a few red things that Hubble couldn't possibly see because they are outside the wavelength range of Hubble, the higher redshift galaxies. But just to show how an image with James Webb would look like. So you can see that James Webb, at the same wavelength, being bigger than Hubble, has a better diffraction limit, so it sees a higher angular resolution. So, gravitational lensing. So suppose you have a big concentration of mass, and you have a source behind it, and you look at it with better and better alignment.
I think there's a stick over there if you want, a pointer that's convenient, just beyond the blackboard.
Oh, yeah, thanks. My eyesight is not that great. Essentially, I have one eye, which is degrading. And it's ironic because the head of the Hubble mission has serious eye problems, and the head of the Future W1st mission has 7 dioptries of correction. So, somehow there may be a connection between how people see and the telescope that they need. So, if the lens is a bit on the side, you are in the regime that we call, I apologize, the quality somehow is not so great, but weak lensing. So your galaxy shape is a little deformed, distorted. Maybe the galaxy looks a little more elongated than you would otherwise be. If it's elongated, it might tilt depending on the alignments. This is the weak lensing regime. This is used to find information, for instance, about the structure of dark matter, and it's a statistical information. You need a lot of galaxies to model what is the lensing field that produces that. Then there is an intermediate regime where you get some funny shapes, and then you have the strong lensing regime where not only the source is distorted, but you get multiple images, depending on the precise alignment. So the key, if this was a point source, is that the angle alpha is essentially proportional to the Schwarzschild radius divided by the impact parameter. So if you plug in the number, the scale for a stellar mass, if this was the sun, is about a microarcsecond of arc. And if you look at, if the lens is a galaxy, is 1 arcsecond, and if the lens is a cluster of galaxies, about 1 arc minute. So this gives the scale. So 1 arcsecond for reference is how large the distance, the Earth-Sun distance would look from 1 parsec, from 3.26 light years away. Or what is it? It's 1 over 200,000 radians, I think. So the other thing, by the way, if the source is a star, is the sun, that means it's essentially symmetric. So the light path all around converge on the same point everywhere you look. So when you look at the source from here, what you see is a ring, which is called an Einstein ring. The diameter is on the scale of this alpha. So the Einstein ring from a star, you're never going to see because it's microarcsecond. You need extraordinary angular resolution to see. While if it's a galaxy, of course, it's less likely for a galaxy to be exactly symmetrical, but if it is enough symmetrical, the Einstein ring will be visible because 1 arcsecond you can actually see. The other point that is will come in later is that the source intrinsic size plays a role. Here we are, so far I've been assuming that the source was the point source, but the source will be extended in general. And if the source size is comparable to this angle alpha times the distance to the source, so if essentially the angular extent of the source is comparable to alpha, different portion of the source will be amplified by different amounts. So if you see a galaxy with a nucleus and the galaxy is perfectly aligned with the lens, the nucleus will be amplified a lot, and the galaxy maybe will not be amplified a lot. So that's a thing to keep into account. So I think I mentioned that typical strong lenses that we see are either elliptical galaxies. These are roundish balls of gas and stars, well, mostly stars, not much gas, except hot gas radiating in the X-rays. And they are roughly symmetrical, and they are tend to be the most massive galaxies around. 10 times the mass of our own Milky Way is not unusual for a giant elliptical galaxy. So they are typically the strong lenses of galaxy nature. The other ones are clusters of galaxies. So these are large group, hundreds or thousands of galaxies. And those are the most massive structures in the universe today. The other thing we have that we call is microlensing. Microlensing would be the case I described, where you have an Einstein ring, it's the lens by, say, a star, could be a black hole, and the whole lens, the whole Einstein ring, is so small that you don't actually see it. You see it just as a single source because it's a microarcsecond in size. So from a practical point of view, you're not seeing a ring, you're just seeing the source enormously amplified. Because remember that gravitational lensing conserves surface brightness. So if what was a small source. Now it's a whole ring. The amplification is enormous, and in fact could diverge if you have if you're really close, perfectly aligned, and the source is exactly point-like. Of course, none of these things are ever true, but you know, it means you can have a lot of amplification. So that's an interesting feature when you have perfect alignment of this type. And I'll mention microlensing later. So what can JWST do? Well, JWST can exploit strong lens. I like the idea of strong lensing because I've taken JWST, which is the biggest telescope in space we've ever built, and I combine it with the largest lenses that there are in the universe. So, hopefully something good will come out of that. So you can exploit time delays from multiple image systems to measure cosmological parameters, and I'll say a couple of words about that. You can exploit flux ratios for multiple image systems to constrain the nature of dark matter. I'll say a few words about that. You can exploit lensing magnification to have an effective higher angular resolution, because with what I said, since lensing conserves surface brightness, if something is brighter, it means it's bigger. You get the two together. The gravitational amplification extends the effective size of the source. So with your telescope, you're seeing more details than you would otherwise. And then exploit magnification to see things that you wouldn't otherwise see, because they would be too faint. And again, let's say something about that too. So JWST, about half of the time of one year, about half a year of observing time is given to guaranteed time observers. These are people that started working at the beginning, soon after the Big Bang. They started working 18 years ago, in my case. I wrote a proposal. I've been working on James Webb, by the way, since 1996. It wasn't even called James Webb. And then there are these ERS, which is early release science. These are people who proposed to do science that will be released immediately in the public domain soon after the data are taken, so that people can learn about JWST data immediately. So these folks are using strong lensing for JWST. This is the number of hours that they are investing in the type. All these folks are using clusters, and I'm also looking at 4 galaxy lenses. So in terms of what type of thing, most people just exploit the magnitude, magnification. They use lensing to see things that are fainter than they would otherwise see. I like to use also the angular, and team also uses the angular magnification. So first thing I mentioned earlier was using the time delay. When you have a gravitational multiple image, say in this case 2 images, you imagine a quasar, QSO, is a quasi-stellar object. It's something that is point-like at the resolution of our telescopes, but we know today that they are essentially black holes accreting mass and converting a fraction of the mass they accrete into energy. They're among the brightest continuously emitting objects in the universe, so they have very bright lampposts that you can see at cosmological distances. And you can do a bunch of experiments on quasars. For instance, there are groups that have used quasars to place limits on the quantum form of the space-time, because you have this thing which is at enormous distance, and the photons come to you, and you can do the experiment. Are the photons coherent when I see them or not? And of course, the effect of decoherence is very small, but you have a lot of Planck length from you to the quasar, and if you work out the numbers in some models that I don't think are particularly interesting, but observations today can rule them out based on the fact that the light from the most distant quasar is still fades when it gets to us. If we had a 100-meter telescope, we would be able to constrain more interesting models. Anyway, we don't. So you have these 2 light paths, and these 2 light paths actually at different lengths. So light from on one path arise at a different time than light from a different time. Now, quasars have some variability. So by monitoring the quasar, you can actually measure the time delay. And I won't spend too much time on this because this is a dangerous audience to show equations to. But essentially, the time delay depends on the redshift, depends on the combination of distances to the lens, to the source, and distance from the source to the lens. Of course, this is a general relativistic thing, so this is not this minus that, or that minus that. Then it depends on the geometry of the systems, and it depends on the gravitational potential in the lens plane, because of course that also introduces a time delay. In simple terms, you measure a time delay that depends on essentially a time delay in distance that depends on the redshift. And if you work out the terms, you have essentially a dependence on the Hubble constant, which is the expansion rate of the universe, and on the cosmological parameters. So by measuring the time delay, you actually get a constraint on the cosmological parameters from one observation. Of course, you'll have statistical errors, but if you repeat it many times, you get better measurement. So you measure the time delay between images, 2 or more if you have more. You have to constrain the potential of the lens, because that, there are a lot of factors here that come into play. And then you connect the delay you observe with the time delay in distance, and so this becomes a constraint of the cosmological parameters. So these are a few plots. This is a quasar, this is the lens, and this is 4 images of that quasar. This is another elliptical lens with 4 images, and this is a doublet. So you study these, you monitor them, and you can derive constraints. So JW, there's this group of which former student is a member who found this name, which sounds like holy cow, for this experiment. Anyway, these are Hubble images. JWST will be able to do the same science with, with better angular resolution and sensitivity. And so what we need to do is to find more lenses. JWST is not the best instrument to find more lenses, but there will be other like LSST or WFIRST that will find extra lenses that can then be studied with JWST. How well can we measure it? This is from some papers that, this is a figure from Rees et al. And this is the type of error that the time delay measurement gives you with 3 lenses. If you had 40 lenses, you could get to this type of error. This is from 70 to 75 for H0. So this is actually very small and very interesting. What is, to me, more interesting, there is debate in this community whether these error bars are too small, because of course, like, the bane of all of us are systematics. So, whether the systematics have been accounted properly. Beyond whether the error bars are realistic or a bit worse, the thing that is important is that this measurement is totally independent of the distance letter and of the cosmic microwave background. So it's it needs one in order to get closure. So it has a completely different set of systematics. That's why it's interesting. It gives you a connection between H0 and the cosmological parameters that is completely different from all the other measurements. That's why it would be interesting if the error bars were a little worse than that because of some systematics. And a possible source of systematics is how well can we model the lens. And there is debate about that. So, suppose we know the lens. What could possibly go wrong with this measurement? If we know the lens, everything is okay. So the uncertainty is characterizing the lens. Now let's move to the second one, the flux ratios and the nature of dark matter. obviously with an astrophysics experiment, we're not going to find the particle, the dark matter particle. But what we can do is constrain the power spectrum of dark matter. So, because let's suppose that dark matter is a regular particle rather than something more exotic for the moment. When that particle decouples, we'll have a velocity. If that velocity is relativistic, it will wash out structure more than if it's not. And so if your dark matter is 3 keV neutrinos, you will be missing structures on the scale of 10 to the 4 solar masses. If your particle is one of the standard CDM candidates, you will have structure power at those scales. So if you are able to measure masses on those scales, you can actually constrain the nature of dark matter. So how do you do this? This is based on the fact that the lens model predicts not only the time delay, but predicts the magnification. You know exactly what the flux ratios of these 4 sources should be if you have the right model. So if what you measure is not what you predict, there are a number of things that could happen. One is that your lens model is wrong. I didn't even include that because how could it be possible? But assuming that the lens model is right, you could have variability. Since the time delay is different, the flux ratios are different simply because you are seeing the quasar at a different time in the different fluxes. But as part of the previous experiments, we are monitoring the quasar to measure the delay, so we can actually rule out variability. And we know what it's doing as a function of time. Another one is the bane of astronomy, which is dust. So dust, however, is small things that are on the way, has a color-dependent effect, while lensing is achromatic. So if you measure flux ratios at different wavelengths, if it varies, it can be dust. If it's the same, it's not dust. The third one is a little more subtle. It's gravitational microlensing. And the fourth one, which is what we hope we can measure, is that there is substructure in the lens and along the line of sight. With lensing, unfortunately, you see the lens because it's the big mass along the line of sight, but there is also a lot of other matter from you to the source, and so that adds up. So you see substructure, and so 4 is the one that we want to study dark matter, because if you have little flux variation can be explained by mini halos that are between you and the source. But in order to make sure that what you see is explained by 4, you need to rule out 3. And the way this is done is you take spectra of your object. You're doing that anyway to rule out dust. But you also do another thing. Quasars have a structure that we now know. And there is gas that's circling around the black hole. Broadly speaking, you're talking about 2 types of gas and a related emission, the broad line region and the narrow line region. The broad line region is broad, which means it has high velocities, large Doppler caused, because it's gas that is physically close to the black hole, and so it moves fast, say several thousands kilometers per second. The narrow line region tends to be gas that is farther out, so it moves at hundreds of kilometers per second, not thousands. Since we have ways to measure the mass of the black holes and we have these velocities, we know the radius where the narrow line region lives, or the broad line region lives. And the resulting thing is that, if you remember, I mentioned that in order to get the magnification, your intrinsic source size must be comparable to that alpha angle. What happens if the narrow line regions are too big to be magnified? So you can rule out microlensing, because microlensing, if you look a narrow line emission, because microlensing would magnify the quasar, would magnify the bromine region, but would not magnify the narrow line region. So if you measure your flux ratio in the narrow lines, and you can see what they are, you are actually measuring something which is independent of microlensing. So the quasar could be microlensed, but by focusing on the narrow line, you are independent of that. And so this is a very nice way of doing the measurement. And on JWST, we have something, I'll say a little more about it, called integral field units. This is done with Hubble by dispersing the light of everything in the field. So it's a rather crude way, and it could lead to, it's not as clean a measurement as it could be. With an integral field unit, essentially it's a device that gives you a spectrum for each point in the image. So that's a very clean way to measure the narrow line region or whatever else you're interested in. There is another technique that I won't say much about. It is to look at how a submass can introduce little wiggles in extended lens sources. It's a similar concept, but it's just a local perturbation due to a halo that you can measure. So both these things are promising, but they would need several tens of many well-studied lenses. So what am I planning to do? This was my program, so I'm not sure why I wrote near is because I'm actually not planning to use it. So I'm planning to use a cluster lens and also to use 4 galaxy lenses for these 4 particular quasars. My official goal is to study the formation and evolution of elliptical galaxies, their progenitors, and their central black holes. I'll now say a few things. So, bottom line is that I will spend probably more than 60 hours of JWST spectroscopy on these fields. For the lenses, my main goal is to use these integral field units that take a spectrum for each point in the image to study a number of things. One, I want to study the kinematics and the properties of the lens galaxy, because the kinematics allows you to improve the model of the lens. I'm also interested in the galaxy by itself. And if a galaxy is in a lens, you get a measurement of its mass that is totally independent of the kinematics. So that's the other reason we want to do that. And I'm also interested in the metallicity, because this is a big topic in the galaxy evolution, how the metal content of galaxy grows. I'm also interested in doing this not only in the lens, but in the lensed galaxy, because of that stretching in apparent size, I get effective higher angular resolution than I would get for a normal unlensed galaxy at that redshift. So that will let me get data closer to the black hole than I would otherwise. I also particularly like this thing, even though it's a pain for reasons we'll see later. This is the lens, this is a doublet, but the quasar has only 2 images, but the galaxy, being more extended, crosses the line where you have 4 images. So in these objects, you actually have 4 images of the galaxy, but 2 of the quasar. So this is, in a way, it's almost a gravitational coronagraph. You are removing the quasar through the gravitational properties of the lens, even though of course you don't go all the way to very close to the black hole. So for these objects, this is the field of view of the integral field unit of JWST, which is 3 arcseconds, and it's magically matched to the size of the sources. As I mentioned, the scale of galaxy lenses is 1 arcsecond radius. So a 3 arcsecond field of view matches well the size of these things. In some cases, you may have to change the orientation to get them more cleanly. And the doublet, the one that has 4 galaxies but only two quasars, is a bit of a pain because it's bigger than the other, so it will require a mosaic. I have to finalize my program in May, so by then I might or might not change my mind. So what about the amplification? I don't have a nice picture of my own, but I'm borrowing one for the other program that uses this, which is JWST. This is an example of how you can reconstruct the appearance of a galaxy from the lens model and the lens image. So you get effectively a lot of under resolution if the amplification is big. This is for an object at redshift 248. So a redshift 2 for lenses magnified by 25, which is not incredibly rare, your physical resolution goes from 500 parsecs to 100 parsecs. And 100 parsecs is a good scale to study giant molecular clouds, which are the objects responsible for star formation. So for instance, for this particular program, that's what they want to do. And it improves, it's a relevant improvement also for other things, like if you're trying to measure the kinematics as close as you can get to a supermassive black hole, for instance, which is more like what I'm going to try to do. The other lens is a cluster. Here, I will take a lot of spectral galaxies that may or may not be lensed, but of course I want to use these as an opportunity to also look at interestingly lensed objects. And an example of this interesting lensed object is that after I picked this cluster, one of the lensed objects in this field was confirmed by ALMA to be a redshift 9.1. And it was already in my target list, and for this object I actually measured the metallicity from line ratios. So that's the type of measurement that I want to do. So clusters used as magnification lenses can give us more information, and this is a big stretch, a bit of an optimistic application. Probably other people, my observations are not ideal for this observation. I didn't tune them for this because I think it's a very long shot, but it's something that other people in the GTO team, like Roger Windhorst, are really looking at. So there is a population of stars that we call population 3. Population 3 stars are stars that have the chemical composition coming out of primordial nucleosynthesis. No object in the nearby universe has that chemical composition. So there must be some population of stars that brings the composition from the primordial to what we see around us. We're pretty confident of what we see. We are pretty confident about primordial nucleosynthesis, so there must be something in between that brings from one to the other. And that's population 3 stars. That's their definition. So they must exist, but it would be interesting to see them and to see if the models of how they are supposed to behave match. And essentially, there are only 2 ways you can detect them, because a single star, no matter how massive, at very high redshift, is very faint. So you can see them when they die, because we think that they die as pairing stability supernovae, which is, by the way, pretty interesting thing. These are massive stars, very hot, and they have electron-positron pairs in their envelopes. And when this happens, the star doesn't like it, because of course, you have a lot of radiation. These are radiation, it's radiation pressure that keeps the star in equilibrium. You produce electron-positron pairs, you remove a lot of energy from the envelope, so the pressure goes down, so the star shrinks a lot. And normally when a star shrinks, it gets a lot hotter, so it makes a lot more electron-positron pairs. So you see that this is not necessarily a good plan for the star. So depending on the details, you can have pair instability as a pulsation or as a straight out collapse, and for some masses it has a couple of pulsations and then it collapses, or or it explodes as a supernova. So in a range of mass, you have a pair instability supernova explosion driven by this phenomenon. And these are pretty bright, but maybe very rare. The other way we could see them is, and this is something we've been working on with my former postdoc who just moved to TCU, is to, if you have enough of these objects, you have a chance that some of them will be strongly lensed by a cluster. So you have a chance to see it directly simply because of gravitational amplification. So this is a plot. I won't bore you with the details, but essentially these are different models and with different assumptions about the background that is present, how you form the pop threes, and so on and so forth. Explaining this plot would be more in line of talks that I've given here years ago. But anyway, the bottom line though is that you have a certain area of parameter space where the star density you expect is of the order of 1 per square arc second. And for amplifications of 100 or 10, they start to be within what is detectable by James Webb. So if a lensing cluster can have maybe 700 square arc seconds magnified by 10, a few arc seconds magnified by 100. So looking at a lensing cluster, in some of these models, you have actually a chance to see a POV3 that is simply magnified enough to allow you to see it. So this is why I'm.
And so
I believe it. Yeah.
It'll just be a different spectrum that reflects a different metallicity.
Yes. Yes. So I believe it enough to write a theory paper about it, not enough to spend my GTO time on it. So observing plans and opportunity. How much time do we have here? I should not on the computer. Okay, 43 minutes in. So we are in 2018. The GTO and the early release folks will be allowed to tweak their program because of the launch delay in May, June. Then there will be a GeoCall will reopen, the one that we closed in December, January. It will be due sometime maybe May in 2020. The time allocation committee will meet that summer. We launch in March 2021. 6 months later, at the end of commissioning, the observations start, and then we start with regular following cycles. So the expected time for writing your next JWST proposal, JWST proposal, is about a little more than a year from now. Just want to spend. Riccardo Giacconi was the first director of the Hubble, of the Space Telescope Science Institute, said something once that I thought was very interesting. He said he wanted to do things in such a way that Hubble would change the way you do astronomy, even if it had exploded on the launch pad. And he created the Guy Star Catalog, which is now used on most ground-based telescopes. He created the first pipelines that reduce the data so that you don't need to be a black belt expert on an instrument in order to reduce the data, and a bunch of other things. And so we try to follow that spirit, hoping that it doesn't explode, but at least improve the way we do it. So we have an astronomy proposal 2, which essentially using JWST would be very similar to using Hubble, with a few tweaks that should make it easier. Similar but easier. We have an exposure time calculator, which is more sophisticated than the one used for Hubble, and we run it on Amazon Web Services because astronomers have this uncanny ability of writing their proposal microseconds before the deadline. So the usage of the ETC peaks about 24 hours before they start writing the proposal, and if you cannot size your computers to run all those calculations. This is very CPU intensive, being more powerful. So we run on Amazon, where you pay as you go. We have more sophisticated pipelines than those for Hubble. We have a new help desk. We have a new documentation system, which is Wikipedia style. Instead of having to read a 600 pages handbook and miss the important point because we're asleep there, this is hierarchical. So you start from the important things, and then you can dig down in the detail as much as is needed. And then we have new data analysis tool, all written in Python, which I personally hate, but that is a different story, and integrated into the AstroPy development world so that it's suitable for input from the community. It's easily shareable and modifiable by the community. And we have data simulators. So status, this is the primary in its full beauty, the 18 segments of beryllium. Somebody asked, I can give them more details than they ever wanted to hear about it. This is the Goddard Space Flight Center, the primary and the secondary mirror deployed. So at the same time, we tested the instrument module. All the instruments are in this package. The instrument module was then connected to the back of the primary here, and in what we now call OTIS, optics and instruments. At the same time, we tested this big vacuum chamber at Johnson Space Center with a simulator for the telescope, I think only a couple of segments to make sure that there wasn't anything bad inside the chamber that would ruin the actual flight hardware. People were developing the sun shield, 5-layer, pretty big. This is a human. And we have a mission operation center at the Space Telescope Science Institute. So then we needed to move these to Johnson in order to do the testing. And how do you do that? You take a big plane, a C5b Galaxy, a transporter that has a 1-inch margin on the side, and you ship it. This is the Johnson Chamber A. At the time of the Apollo program, that's what it was used for. And this is when JWST was tested in there. It's a very interesting thing. It was declared a national monument after Apollo, so we had to obtain a waiver from the National Park Service in order to modify it.
Is that actually the primary folder? What are we seeing that's being?
This is the primary and the secondary with the
The real
instruments
thing.
in the
It's
back,
not
the real
just
thing going into.
It's not just a mock-up.
No, this is the real thing going into the chamber. This is the chamber door closed. This is a massive door, by the way. It's really impressive to see. This is the temperature inside the chamber, and this is the temperature outside the chamber. This was a test of about 100 days to test the instrument. A lot of it is cooling to helium, to liquid helium temperatures, the structure this size. The unfortunate thing of having mid-IR is that you cannot cool it to liquid nitrogen. That is a technology which is 77 Kelvin, which is a technology is very easy. You need to cool it to 40 Kelvin, and for that you need liquid helium. And that's a whole different ballpark. We were talking about multiple trucks of liquid helium a day to keep it at that temperature. And so it was a 100 days test, and we had a hurricane hitting Texas while we were doing the test. And there was flooding, there was, so we, cost us 2 days delay, the hurricane, but the hardware was undamaged. This is a picture from the thing inside. This, I won't say much, but this is an image of the segments that are not aligned yet. Of course, one of the things we need to do is align them. And for people who want to know, we use what's called dispersed Hartman sensing. But this is the primary mirror aligned. This is a phase diagram. Essentially captures the phase differences from pixel to pixel. So something like that equals good. This is an example of a deployment. This is a radiator on the back of the instrument module. The mirrors are on the front or the side when it's folded. And this is a radiator. So a lot of tests happen on the ground. This is the flight instrument and telescope. Now it's a Northrop. And this in the back is the sun shield that is being prepared in folded configuration.
Are the things that look, well, they're yellow but are hexagonal, or is that actually the pixel? I mean,
Yeah, these are the mirror segments.
Mirror
It's-
segments? And what's on them?
It's beryllium coated in gold, because gold is,
And that's just exposed to the air in that picture.
well, gold has a
Yeah,
good
I
property
guess
that
so.
it doesn't care. But yes, yeah, we are very careful. Contamination, aside from my joke, is a concern. Not so much because you are afraid that it will be corroded, but because dust grains can deposit on surfaces, it can thermally decouple, and then you can end up in a situation where a dust grain ends up being much warmer than the rest, and it starts being a source of infrared radiation that disturbs you. So this is monitored very carefully. So this is an example of the sun shield being, it's a test. So here, this is a simulator of the instrument module. The instrument module hasn't been connected yet. And these are the so-called unitized power structure. Whatever it is the thing that contains the sun shield. So this is one part deploying and one other. So we do a heck of a lot of tests. And this is further testing, and this is how we fold it back. Turns out that folding it back is harder than deploying it. And since we deploy many times for testing, the folding it back has to be done multiple times, and that's one of the reasons of the launch delay. It takes a lot longer to fold it than we thought. On the other hand, I don't know how many in the room have jumped out of a perfectly functioning plane, but if you are doing skydiving, or if you use parachutes, you know that folding the parachute is very critical. A lot of the people that do it regularly like to be the ones who fold their own parachute, because the vast majority of the accidents happen because something went wrong in the deployment, is because it wasn't folded right. So you want to deploy it right, so you have to fold it right. That's essentially what, and you don't want to take any chances. So this is again a picture of the thing fully deployed. This is an example of how you work. We have these boards, and people that have to access the structure use these diving boards to it's not a very natural and convenient way of working. That's another reason why it takes a long time. You want to make sure nothing bad happens, you don't drop a hammer or anything. I mean, it's unfortunately, so this is when it finally launches. This is how it looks like inside the shroud. So the bottom line is that we are now planned for launch in 2021. We are actually working to be ready in November 2020, but then there are 4 months of reserve made by NASA headquarters. The instrument and optics have completed all tests and have passed the final test. So the instruments and the mirrors are done. But now we have to finish the sun shield and the spacecraft module, the thing that contains communication, propulsion, and so on. And there are no known technical issues, and the delays that have happened have been due to complexity that have been underestimated, and to human errors that, if I was, is this webcast? No?
It's recorded.
Is recorded. Okay. And human errors that unfortunately.
Can I ask an engineering question from the very first part?
Yeah.
So you have this micro machine thing that opens and closes slits,
Yeah.
but why not just use like a MEMS device, like a DLP? Like, why do you need to open a slit and not just deflect it?
That hurts. So, initially NASA funded 3 teams to look at what was the right slit selection mechanism. One was the Goddard team, developing microshutter arrays. 2 were DLP-style things. The Texas DLPs, as is, they are not okay because they are 16 microns. The micrometer is 16 microns. And you don't want to use a 16 micron thing at wavelengths of 5 microns. Too small. And so we needed a 100 micron or a 200 micron mirror. So 2 teams, one based at Sandia and one based at Goddard, were developing micromirrors. The one based in Sandia was silicon-based micromirrors. Silicon, well, has their problems because silicon has the unfortunate feature that it doesn't reflect infrared light that well, so it needed to be coated. And once you coat something at these sizes, you have what's called the potato chip effect. You know, surface forces are very strong on the small scale, so it became a major engineering problem. The other group was using, like the Texas Instrument DLPs, was using aluminum micromirrors, and I was part of that team. So we were building micromirrors for this, using one of the TI people as a consultant to avoid making mistakes. Once we had a nice discussion, I said, well, you know, I've done some modeling, and you know, the Texas Instrument micromirrors tilt on the diagonal. They don't tilt on the side. And I said, well, I did some modeling. Is it because if you tilt on the side, you get diffraction in this and this way? And he says, you know, that discovery costed us $500 million. So anyway, sometimes it saves money to do a little optics modeling. But anyway, we were not selected because there was the fear that the design of the spectra would get bigger and that there would be too much scattered light. I disagree with the choice, but obviously I'm not exactly impartial. So we were not selected, so ended up the microshutters were the one that were considered the best option.
How much of a concern is intercluster light when you're looking at these lensed images, when your foreground lens is a cluster? Or is the magnification sufficient enough that it outshines the ICL?
So the typical, the concern about intercluster light, yes, it's outshine. There are though problems of having a cluster because it generates extra objects. So you could have contamination for other, dwarf galaxies in the cluster. And the other one is that if you really want to use that technique to study extraordinarily faint POP3s that are enhanced, you have to be sure that you are not seeing a supergiant in the cluster. So, some of these things will be so faint that you cannot actually take a spectrum. You would have to take a spectral energy distribution at low resolution. So, it could be slightly tricky, but probably if you are trying to recover, depends on what's your goal. If you're trying to recover the physical structure of the galaxy by reconstructing its shape at higher resolution, then how well you can model the cluster lens, because it's a more important problem. For some of the ones where you go to the fainter sources, the contamination could be a problem. Thank you.
There are no other questions. Let's thank Mr. Stiavelli again, and remember that there is wine and cheese on 10:45, and we can continue the discussion over there.